our tutor is here. Her name is Delisha Davis. 1 second, let me turn off share screen. Okay, cool. There we go. So good afternoon, everyone. Thank you for tuning in. This is the fourth refresher session for Chem, or overall. So this one is for Chem. We also have physics tomorrow if you're in electricity and magnetism, and we're going to touch a little bit on modern physics. Thank you for tuning in. Your tutor is Delisha Davis. Firstly, I want to definitely thank her for taking the time to put these questions together and be willing to be here to go through with each of you. So if you have any questions, if you have any queries at all, just let her know. You can either send it in the chat or you can turn on your mic briefly and then ask the question and go through. Also, if you guys have any questions regarding how school will continue next week, after the session, you can definitely just let me know and I'll go through some of what the guild would have said in the town hall earlier. So again, thank you for showing up. I guess my name is Danielle Mullings. You guys would have seen that on the screen already. But yeah, so let's say a nice welcome to Delisha, who's gonna take over from here.
Hi guys. For most of you should already know me. I'm usually your organic tutor. So for today, we're just doing some practice questions. So
we're barely hearing you.
You're not hearing me?
I'm hearing quite clearly.
Yeah, I'm hearing clearly as well.
Okay. So for today, we will just be doing some practice
questions. I guess it's a signal.
Probably. I'm sorry. I'm putting a microphone. No? Are you hearing me better now? No? Okay. All right. So let's jump into question one. Question one is an chemical equilibrium.
Right, like it's giving an inner feedback.
Okay, the person who's having the problem, you can just WhatsApp me and you know, I'll talk with you and figure out how to get it working.
Can you hear me better now?
Hello? Yeah, I can hear you clearly, so I think you're good.
Okay. Okay, so question one is hyperbromous acid has a Ka, which is, is their equilibrium constant of 2.8 times 10 to the minus 9. How would you go about calculating the pH, the concentration of all the species present? And yeah, so those include the 4 different species that I have here. And this was taken from a past paper, 2013. So I think we covered this also in the last tutorial, either the last or the second to last. So let's just go back over it. All right, so the first thing that you would want to do is to write down your equation, right? Initially, the question told you that at the start of the equation, at the start of the reaction, there is 0.2 moles of your hyperbromous acid. Since you're using water as a solute, as a solvent, then you don't have to put in. You won't, that's basically an infinite number of moles of water in comparison to the acid. So you will not put that there. Let me look at my pointer. 1 minute.
Wait, sorry for interrupt you, but you couldn't repeat for yourself, please. But you just got from a book and pencil. Write down any important thing where they say, but it starts, yeah.
Sorry, give me a minute. Okay. So we had just begun. So what I was saying is that the question one, this is a chemical equilibrium question. We did this in the second to last or the last week of tutorials. So this is just a refresher for you. All right. So you're told that hyperbromous acid has a Ka, which you know is an equilibrium constant of 2.8 times 10 to the minus 9. You're asked to calculate the pH along with the concentration of all the species present at equilibrium, right? And you're given the concentration of the hyperbromous acid, all right, at equilibrium. So to go about answering this, the first thing that you would want to do is to write down your equation. As with almost all chemistry questions, you first just start off with your equations. Initially, you're told that you have 0.2 moles of hyperbromous acid, right? At that point, you know that you would, remember that reactants goes to form product. So at the beginning of your reaction, you would not have any reactant. So initially, you're 0.2, but your reactants would have been 0. That will be the concentration. At equilibrium now, let's say you have a change. So let's say X amount of your reactants goes to form your products. Since from your chemical equation, you see that it's a 1-to-1 molar ratio between your reactant and your product, that means that whatever loss you lost in your product, whatever concentration or number of moles that have been lost from your reactant, that must have been gone to form products. So if you lose X number of moles of your reactant, then you must have gained X number of moles of your product because it's a 1-to-1. So if we say that we have lost X number of moles, and therefore what you would have at equilibrium for your reactant would have been 0.2, which you were told that this is what you started off with. So it would have been 0.2 minus X number of moles. Hence, the number of products that you would have formed at equilibrium would have been X for each of them. All right. You would know that the equilibrium expression is your products, the concentration of your products over your concentration of reactants, right? So if we're using that, then we would have our two reactants, the concentration of our two reactants of our two products over the concentration of a reactant. Now, in this case, we're using water. But water is a pure liquid, and as you would note, or as you would already know, you would not include that in your equilibrium expression. As such, we simplify our equation to this that you're seeing. Now, at equilibrium, remember that we have said that we had X amount of each product. So by putting those into our equation or expression, we have X times X all divided by 0.2 minus X, which would have now been our concentration of our reactant at equilibrium. We are also given the equilibrium constant. So if we jump back up, you would have known that you were given an equilibrium constant. So we're putting that into our equation as well. Now, a rule of thumb is this. If your equilibrium constant is very small, therefore any changes that you would have made to the concentration during equilibrium would have also been very small. So if, let's say, for example, you have 1 minus a very, 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 very small number, then it's almost the same as 1, right? And so, in this case, since we have 0.2 minus X, we're assuming that X is very small since the equilibrium constant itself is very small. And therefore, 0.2 minus X would have been approximately the same as 0.2. With this, we can go ahead and simplify our expression even more, right? So hence Ka now, our equilibrium constant, now becomes x squared divided by 0.2. And we know that our Ka was 2.8 times 10 to the minus 9. Hence, if we just solve our equations, we make x the subject of the formula. So it becomes x squared equal to 2.8 times 10 to the minus 9 times the 0.2. So what we basically did was to turn 0.2 up. And then we square root our x squared. Whatever we do to one side, we simply do it to the next. And so x now becomes 2.366 times 10 to the minus 5. Is everybody clear with this? Any questions?
For the Saturday, okay. For the 0.2, where that come from again?
Okay, so you were told that in a question. So let's go right back up to the start. So you're told that at equilibrium in a 0.2, so hyperbromous acid has a Ka of 2.8 times 10 to the minus 9. You're asked to calculate the pH and the concentration of all these species at equilibrium in a 0.2 mole, in a 0.2 molar aqueous solution. So you were told that in a question.
Oh, okay, all right, I get that. Yeah.
Everyone is understanding? All right, so we do. Right, let's give you guys a moment to take that in.
One question.
Mm-hmm.
So where you have 0.2 minus x is approximately equal to 0.2. Will that be the case for most of these questions?
Yes, it will actually be the case. Remember that if you have most of your equilibrium constants will be very, very small. It's normally some number, the minus 10 or to the minus 19. Some of them are even way very small. If you can look back at almost all the questions. And so once the equilibrium constant is small, then it goes to show that any changes that is normally made
Miss,
to the reaction equilibrium is normally going to be very small.
you can
Yes?
go in. Okay.
Okay, thank you.
Okay. Hello? Someone else
Miss,
was
I'm not
asking a
sure if you're
question?
hearing me also, but you kind of went in and out a while ago. So I wanted to ask, you're hearing me,
Yes, I'm hearing you.
Miss?
I'm hearing you.
Right? Where it says
Go ahead and ask the
x over
question.
x, because right, yeah, the signal where you have the x over x times x, sorry, over 0.2 minus x. Why subtract the x?
Mm-hmm. Why what? Why do I have X?
Why you subtract the x?
Okay,
Why
so
subtract
it goes
the x?
back. Oh, you see my pointer?
Yeah.
Okay. So remember that we were told initially that we have 0.2 hyperbromous acid starting with, right? So this is at the start of the reaction. What happens at the start of the reaction? You add reactant, and then over time it becomes product, right? Okay, so you're starting off in your vessel, in your beaker with 0.2 mole of molar concentration of hyperbromous acid. Over time, it changes until the equilibrium is attained, right? At the change of your at the equilibrium, you don't know how much the change is. And so we assume that X is your change, right? You could have used A, you could have used B, you could have used any number, any
Okay.
letter.
Yeah.
You
Okay.
assume that X is
Yeah. Understood. All right, Miss. Yeah.
okay. Any other question? No?
No, miss.
Can I move on or you guys need some time to write?
I'm just writing it down. Give me a second.
Okay.
I can go.
Okay. Okay, so if x is equal to 2.366 times 10 to the minus 5, remember you were told to find out the concentration of your two reactants, of your reactant, one reactant, water, we don't use water, and your two products, right? Along with the hydroxide ion concentration that is formed. So, coming back to your equation, or to your reaction equation, as we said, X was also represented both of our reactants, both the hydroxonium ion and your anion that is formed, your conjugate acid would have been represented by X. Therefore, the answer for X would have been also the answer for these two. Right? However, now, and then you would have known from the start that your answer, the concentration for a hyperbromous ion acid would have been your 0.2. Because remember, if you have 0.2 and you even minus X from it, so if someone happened to calculate and they just minus 0.2 minus X, the answer for X, you would have seen that if you're working back down to the amount of DPs that we're using here, then it would have been almost the same as your 0.2. So the answer for the hyperbromous acid also. We get up to here, right?
Miss, you can repeat that part again, please?
Since the X represented the concentration of your two reactants, right? Your conjugate acid and your hydroxonium ion, then these, therefore, the concentration of these would have therefore been the value for X, which is 2.66 times 10 to the minus 5 molar. So we do that. All right. Next, you're also asked to find out the concentration of your hyperbromous acid. You were told this in the question. So if you go back to the question, you say hyperbromous acid having an equilibrium constant of this. Please calculate the pH and the concentration of all these species at equilibrium in 0.2 molar. Remember, we assumed that the change in equilibrium was so small that it did not really affect the value of the hyperbromous acid.
Yeah.
So therefore, at equilibrium, the concentration of the hyperbromous acid would have been 0.2, just the same. And if you want to be technical, you can minus the X from the 0.2, and you can look to see that it almost approximates to be the same thing.
Okay.
Right, I didn't do it. Let me do it and tell her the answer. 0.2 minus, okay, 2.36. The answer is 0.1999734. If you round it up to 4 significant figures or 3 DPs, you can back approximately 0.2.
Okay.
You understand?
Yes, miss.
All right. Then now to determine the concentration of your OH ions. All right, you're going to go back. I don't know if you remember this expression. The equilibrium constant for water is equal to the concentration of your ion, the hydroxide ion and your times your hydroxonium ions. And the equilibrium constant of water is 1 times 10 to the minus 17, room temperature. So if you know that for expression, then we can just plug in our values. We know the value for the hydroxonium ion here, which we just calculated from here. You plug that in, and you made the concentration of hydroxide, the hydroxide ions, your subject of your formula. That would give you 4.23 times 10 times 10 to the minus 10 moles per gram. And then to find pH, pH is simply the minus log of the hydroxonium ions concentration, and that would give you, plugging in that into the formula is 4.63. Any question?
Hello.
Yes.
Yes. Quick question. What is KW again? What does it represent?
It's the equilibrium constant for water.
Okay. Thank you.
The Ka is the equilibrium constant of the acid. Kb is the equilibrium constant of
Thanks.
Kw is the equilibrium constant of water.
Yeah, I forgot that. Thank you.
You know, the equilibrium constant for water is normal 1 point, is 10 to the minus 14.
All right. To be honest, I'm not really, probably I true, but I look on it properly, but I'm not really understand. You could just a brief summary. I'll write your side again, please.
All right, 1 minute. Okay, do you want me to, did you understand the first part? Hello?
Which first part? You mean the paper before this? The page before
Yes.
this? Yeah.
Before this. Okay,
Yeah.
so this is a part that you don't, do you understand up here why we could say that the concentration of the conjugate acid, which is Br minus, and the concentration of the hydroxonium ion, which is H3O plus, would have been both equal to 0.2. Would have been both equal to 2.36 times 10 to the minus 5.
I'm gonna think more understand
that?
From everything right here, so
Understand this part
everything on this page.
here? You got everything here?
Yeah.
Okay. Now look back to this line. Remember, this is what happens at equilibrium. At equilibrium, the hyperbromous acid increases in concentration. Can you turn on whoever that is? Can you just turn on the background noise, please? Thank you. So remember, at equilibrium, this is what happens. Whatever concentration of your reactant that is actually used up, you're assuming that that goes to form products, right? So we're assuming that there's no side reactions that is being carried out here. So all of the reactant that is used up goes to form your products. So if you started off with 0.2 moles of your reactant, or 0.2 molar of your reactant, then whatever you've lost during the reaction of your reactant goes to form products. So if you have lost X number of moles of your reactant, and you're assuming that X number of moles or X concentration of your products are formed, right? Especially due to the fact that you have a 1-to-1 mole ratio. So 1 mole of this goes to form 1 mole of this and 1 mole of this. Understand?
Yeah.
Hello? Good. So therefore, At equilibrium, we're assuming that we have X number of moles of of your conjugate acid and X number of moles of your hydroxonium ion. Okay? So,
Yeah.
and X is what we carry through, all the way through, to find out what exactly is X. So if X is 0.2, if X is 2.366 times 10 to the minus 5, then therefore remember that X represented both this and it also represented the hydroxonium ion. So therefore the concentration of these two would have been valid for what we just found X to be. Which is what we did right here. Hence X is equal to, if X is equal to 2.366 times 10 to the minus 5, therefore, I probably should put concentration here. The concentration of the conjugate acid is also equal to the concentration of the hydroxonium ion, and that is 2.366 times 10 to the minus 5 molar. Do you get that part so far?
Yeah.
All right. Since we said around here that once the Ka, once the equilibrium constant of the acid is small, and you can see that it's small by the value that they gave you, 2.8 times 10 to the minus 9, right? So since the Ka is very small, whatever change that would have been made to the concentration of the reactant would have therefore been very small, very, very small. Hence, if we have 0.2 moles of the reactant starting off with, therefore 0.2 moles, and you have changed, you have assumed that some of that have gone to form products at equilibrium, that change will be very small. And so you can basically look aside from that change and just say that, okay, it's still approximately 0.2. And you can prove that. Remember, we calculated X to be 2.366 times 10 to the minus 4. So if we say 0.2 minus 2.366 times 10 to the minus 5, the answer that we got, the answer that I got was 1.9997 something another. I didn't, 1.997634, which is approximately the same as 0.2. Hence, the concentration of your hyperbromous ion at equilibrium, so these are what you're finding, right? The concentration of a hyperbromous ion at equilibrium will have never been approximately the same as 0.2, which is what we did right here. And then you're asked to determine the hydroxide ion concentration. Using your expression of Kw equal to hydroxide ion concentration times your hydroxonium ion concentration, and this is equal to 1.10 to the minus 4 at room temperature, you just plug in the values because they already calculated this, and you were told this, and you should know this, 1.0 times 10 to the minus 14, and therefore you just solve to make the hydroxide ion the subject of the formula. So this expression up here is known. So this is just a matter of you actually knowing this expression. To find that the pH now would be, this expression is again known. pH is equal to the minus log of the hydroxonium ion. You already found the hydroxonium ion concentration, so all you have to do is plug it in, and you would have gotten that. It is 4.63, so therefore you know it's less than 0, and you know you're dealing with the acid, so therefore you know you're on the right track. You understand now?
Yeah, I think so, miss.
All right, just take some time afterwards and just go through it. Most of you guys, I think, will have my email, so.
Miss, the expression of KW is always given.
KW
Yeah,
is
do
always the hydroxonium ions times the hydroxide ion. And that is always, KW is always, once pure water, remember, it's an equilibrium constant of water, of pure water.
oh,
So
okay.
once it's pure water, then it's always 1 times 10 to the minus 14.
All right.
Excuse me, miss.
Yes.
Would it be possible for you to reiterate your email? I think I misplaced it somewhere.
Okay, my email is just simply my name. So it's normally the same UE email format. My name, Delisha.Davis, and you according to UE format. So my name is Doleasha. That's Doleasha. Davis, Davis. And it follows the UE email format. Are we good?
Yes, miss.
Yes, miss.
Yes, ma'am.
All right, so question 2 is kinetics. Everyone here got the chance to do the last lab? I know further people would not have done it. Do I have any further people here?
Yes, miss. Whenever, yeah.
Okay. All right. All right. That's all right. All right, so question 2 is from kinetics. And it states that the initial rate listed in the table below were measured in methanol for the reaction, right? And you're given the reaction equation above. Hope it's big enough for you all to see it. And you're given a series of 3 experiments. So let's explain this a bit. So this is the reaction you're doing, right? You are reacting this reactant with iodine, with iodide ions to form these products, right? What we have done right here is to simply change the concentration of the reactants one at a time. So in experiment 1 or run 1, what they did was to change the concentration of this, right? Dibromethane, right? So they change the concentration of dibromethane, which is, let's call it reactant 1. And they have 0.051 as a concentration of your iodide ions. That would have given you a rate constant. That would have given you a rate. Then what they did was to keep the concentration of your iodide ions constant while changing the concentration of your dibromethane, right? So if you realize here, the concentration of iodide ions are 0.051, 0.051. However, what's changed is the concentration of your dibromethane. Don't pay attention to the rate yet. We'll come to that, right?
Let me go over that again.
So what they're trying to do right here is to determine the rate law. I'm going to go through what a rate law is in a minute. I'm just explaining what they did. So what they did was to take a reaction and then they change up the concentration of the reactants one at a time. So let's say they start off with A plus B going to form some product C. What they would have done first is to carry out the reaction as it is, right? Use the concentration for A that they want, use the concentration for B that they want, right? However, they would have redone the experiment, changing now the concentration of only one of the reactants. So let's say they keep A constant. So whatever they did at the initial, they would have kept that concentration the same for A now in the second experiment or in the second run. So A, the same concentration will be for A now than as it was before. However, they would have now a concentration of B. And then they would run a third experiment where they kept B constant and changed the concentration for A. What that does is allow them to determine the order of the reactant. Let's look at this one that we have. So the experiment 1, run the experiment. They use concentration of the dibromethane as 0.0635. For the iodide, they use 0.051, right? In a second trial or in the second run, what they did was to keep the iodide ions constant to realize the concentrations are the same in run 1 and run 2. But now they change the concentration of the dibromethane. For run 3, what they did was to keep the concentration of your dibromethane constant, so it did not change between 2 and 3, but now they change the concentration of your iodide ions. We're going to look at why that is important. But first, let's just go into some background. So background information, what is the rate law? So the rate law is the relationship between the rate of the reaction and the concentration of the reactants, right? So it's how does the rate of the reaction change as you change the concentration of the reactants? How much, or in another way, in another sense, is how much is the rate of your reaction dependent on each reactant concentration? Let's say, as I was saying before, let's say we have a reactant A plus a reactant B plus a reactant C going to form some products D. The number of moles of A is lowercase a, the number of moles of reactant B is lowercase b, and the number of moles of C, reactant C, is lowercase c. Your rate now becomes, your rate law becomes the rate equal to the reaction constant times A, the reactant A, times the concentration of your reactant B, times the concentration of reactant C. What you should note is this. The equilibrium constant expression is not the same as your rate law expression. So if you remember your equilibrium constant expression, this is normally derived from your balance equation. So your equilibrium constant expression, which is what we just did before, is your equilibrium constant equal to the concentration of your reactant C. I didn't correct this one. I didn't put it, there should be C down here. Give me a minute. Okay. So your equilibrium constant expression for this reaction would have therefore been your product D raised to the number of moles of D, all for your reactants A, B, C, individually raised to the number of moles of A, B, and C. However, that's not your rate law expression. Your rate law expression is simply the rate equal to the rate constant times the concentration of the reactants raised to the order of those reactants. And those orders have to be found out experimentally, which is why they actually did these series of experiments. So you first ask to determine the rate law. So with this in mind, we therefore write the rate law expression for what we have here. So remember, your rate law is a rate equal to the reaction rate, to the reaction constant, times your reactants, right? So we have a rate. So we have a rate equal to a reaction constant times our two reactants. That's our dibromo ethene times our iodide ion, right? And now we're raising it to the orders. We call it X and Y because we don't know what X and Y is. That can only be found out experimentally. It's not the number of moles of your two reactants up here. That is what you do for your equilibrium constant expression. Your rate law is completely different. All right, so the first thing you want to know is, how do I find the value of X? So to find the value of X, you're going to look for two experiments in which a concentration, so X has to do, in this case, X has to do with your dibromo ethene. So that is an order of reaction with respect to your dibromo ethene. So you're going to look at your experiments that you have, and you're going to try to find two experiments in which your other reactant, or your other reactants, if you had more than one in another scenario. So you're going to look for two experiments in which your other reactant is constant, the concentration of the other reactants are constant. So if we go up here, then we would have realized that our other reactant in this case would have been your iodine ion, and in 1 and 2, they did not change. The concentration of our iodine ions remain constant. Hence, to find the value of X, we simply divide the second experiment by the first experiment. So you fill in the values that you gave us. Rate would have been 6.45 times 10 to the minus 5, equal to the concentration of your dibromo ethene would have been 0.0635, and the one for your iodine would have been 0.051. You do the same thing with your expression, with your rate expression for experiment 2. And then, as I said, you simply divide the second by the first. So by dividing your second expression by your first expression, what you would have realized is that your rate constants are cancelled out. Not only is your rate constant cancelled out, but also your concentration for your iodide ions would also have been cancelled out because they're the same. So if you divide 0.051 by 0.051, it would have been 1, right? So it would have been cancelled out as well, and your Y would have been cancelled out. So what is left now is a simplified expression where you only have the rates being divided by the concentration for one species. Or the rates where you have one expression only having a concentration for one species, not two. All right. So what would have happened? What would have happened is that you would have had what would have happened is that you would have had 1.75. You would have had 1.74 times 10 to the minus 4 divided by 6.45 times 10 to the minus 5, right? And this would have been equal to, you would have also divided the right-hand side of the expression, right? That would have now given you 2.70 equal to your 0.172 divided by your 0.635. From mathematics, you know that if you have two numbers raised to the same powers, then you can just divide those numbers and then raise the answer to the power, right? Like what I did here. Once you get that, you get a simplified equation and you log both sides. What you would also know from mathematics, from indices, it would help if you have some appreciation of mathematics, is that once you log both sides, once you have a log of a number raised to a particular power, then that becomes that power, the power times the log of that number. So if you look at these two, so just look up your laws of indices. Once you have a log raised to a particular number times a power, now what you can do is put the power before the log of that number. So these two expressions are equivalent. Once you have that, you can divide now by log of 2.71. And what you have is x equal to 0.996, which therefore means that x is equal to 1. You guys have any question with this? Any questions?
Yes, miss.
Okay.
Could you use equation 2 and 3 and get the same answer or no?
If you use equation 2 and 3,
I mean, experiments 2 and
all
3, sorry.
Hmm?
Experiments 2 and 3, sorry.
Experiments 2 and 3. If you use experiments 2 and 3, what you would realize is that the dibromine 18 is kept constant, the concentrations. What is changing is your iodide ion concentration. So what you would have canceled out here would have been your X. So what you would have found is your Y, which you will have to find your Y anyway. You could have opted to do.
Okay.
Any other question?
Okay. Oh yeah, go find the value of x. Yeah. All right.
So just confirm then. Over on the 4, I'm seeing that's basically we divide 1.74 times 10 to the minus 4 by 6.45 times 10 to the minus 5 to get the 2.70.
Yes.
Okay, just making sure. Thanks.
So this. Okay.
Yeah.
Any other questions? Okay. So now that we found
The
X.
signal, the kind of job.
Okay.
Right now, I was saying that the signal fell, and I heard the students asking previously, in what case do you use
In what case do I use which expression?
no experiments 2 and 3?
Okay, so what I was saying, my answer was that you use experiment 2 and 3, but look at it. What's kept constant in experiment 2 and 3? The concentration of your dibroma 18, 0.172, right? So if you plug all of these values in here, what you would have canceled out would have been your dibroma 18, hence would have canceled out X. And what you would have found would have been Y, which is not bad because we will have to find Y anyways. So if you want to find Y
Okay,
first,
understood. Yeah, we were asked to find. Right, let's get it. Yeah.
Any other questions?
Miss, I realized when I did like how you did I set it out experiment 3/2. When I did the opposite of that, I got the same answer.
You got one.
I got the one, yeah.
The same answer.
Yes, miss.
All right, let's go. Let's do it. All right, so if you're gonna find, so I'm on the next page now. So now I'm finding Y. All right. So we're gonna divide experiment 3 by experiment 2, right? So now our 0.172 has been canceled, leaving me with only my concentration for my iodide ions, right? 0.174 times 10 to the minus 4. If you realize, we also have the same rates here, right? So therefore, when we divide our rate of experiment 3 by our rate of experiment 2, if you divide the same number by itself, what do you get? 1, right? And then now what you have is you have your right-hand side of the equation, right? Which you have 0.051 divided by 0.0625. That when you divide that, I got 0.816. What did everybody, is that what everybody got? Is that what you got?
Yes, miss.
Okay.
Yes, miss. Yeah.
Once you raise that now, once you log both sides, log 1 is equal, or let's wait first. Once you log both sides, then you just do the same thing, the mathematical expressions. You know that once you have a log of any number raised to a particular power, then the power now comes before that log of comes before the log of that number. I can just times the log of that number by the power that it was raised to. Once you do that, you would have had this expression. So now what you would have done would be to divide by a log of 0.816 to get your y being the subject of the formula. If you put this into the calculator, you would have known that the log 1 would have been 0. So 0 divided by any number would have been 0.
Okay, understood, Miss. Thank you.
Are you guys understanding that?
Yes, miss.
Yes, Miss.
Yes, miss.
Yes, miss.
Definitely.
Yes, miss.
Okay. So therefore, all of the reaction with respect to iodide would have been 0. It meant that iodine did not affect the rate of the reaction. Hence, your rate law becomes now your complete rate law would therefore be the rate times a constant times the reaction constant of your dibromethane raised to 1 times the concentration of your iodide ions raised to 0. You know that once you have something raised to 0, let's say 2 raised to 1, 2 raised to 0 is the same as 1. You can put that into your calculator, you realize that once you have anything raised to 0, it's the number itself. It's 1 itself, I mean. Hence, this would have been canceled, that would have been 1. And you know that anytime you have a number raised to 1, it's the number itself, and hence you don't have to write the 1 up there. So the simplified rate law becomes that. That means that the only thing that is determining the rate of the reaction would have been the dibromethane. Any question?
No, Miss.
Does it matter which order we divide by? For example, number 3 where it says divide the third by the second. Can we divide the second by the third instead?
Divide the second by the third, what would have happened would be that you would have gotten a negative sign, but I think it should work out to be the same. You can play around with it and find out.
Okay.
Anybody else? Any other questions? Well, let me give you a minute to write it off then.
I don't think so, no, miss. But me not have no other question. Me not have no questions.
I'm just giving them a minute to write it off. Let me know when you guys are finished. Right now.
Miss, I'm finished.
Finish?
Yes, ma'am.
Finished, Miss. Thanks.
Okay. All right, so the other parts of the question asks, what was the value of the rate constant? So if we use any one of the experiments, whether it be experiment 1, experiment 2, or experiment 3, then you can use any one. I use experiment 1. So you simply put in the value of the rate, the value of the rate that they gave you, and plug in the concentration of your two reactants, raise it to the order in which you just found out for the rate law. And once you do that, plug it in, you would have canceled out this part because you know any number raised to 0 is simply 1, and any number raised to 1 is simply itself. You would have gotten this for your rate constant.
Miss, can you repeat that one, please?
So you're going to use 1, right? Once
Yes,
you
Miss.
plug in the values you have for experiment 1, so remember that your rate law is equal to the rate times the rate times the two reactants, the concentration of the two reactants raised to the order of those reactants, right? And we
Yes,
just
Miss.
determined that this over here, right? So
Oh, yes,
what we're
Miss.
going to do is, what I did was to plug in experiment 1, the values for experiment 1, into my equation here, and solve to find K.
Okay, understood, Miss.
Excuse me, miss.
Yes?
I am not seeing any they call again units.
I didn't work with any units because they didn't give any units on the question. But if you are actually given a unit, you
I
have to
think I saw
provide 1
something
unit.
at the bottom said they will be giving marks for the units too.
Which one? Where is it? Oh, let's go back. Hmm.
On the worksheet, it says, note briefly, marks are allocated for correct units.
All right.
Yeah.
Let's see. Which one is this? Oh yeah, sorry, my bad. So the units here was big M, which you know that big M is equal to moles per dm cube. And then the unit for the rate would have been moles per dm cube per seconds. So let's calculate that. My apologies. So this will be moles per dm cube per second, so big M per second. And if this is big M and this is big M, that will be in one. Let me just work that out. Are you still able to see my screen?
Yes, we are.
Yeah.
People let them in the meeting.
Must see if that becomes correct.
Yeah, so why is one M squared and the other?
Oh, let me just do it this way then. Is that what you got?
Miss, we get M squared from?
What I did, because I put in this. So if we have 0.051.
Repeat that, miss?
If we have 0.051 moles per dm cube raised to the 0 power, it's still going to be 1. So it's going to be 1 moles per dm cube then.
Oh,
right?
I thought the M would be cancelled out.
I mean, if you got 0, then it would be cancelled out, but it's 1. So you still have the units.
So
Oh, okay.
Okay.
Right? And then once you divide through, you get per mole, and you would have still
This
had
is
your per
still lost
seconds
because
here.
I don't know if it's a signal.
I'm not sure. Maybe it's your signal. I'm not sure.
Miss,
Yeah?
where you have 0.0635 m to the m squared. I don't understand how you get m squared and not just m.
M times M.
Oh, yeah.
Okay. Another question? All right, so the last part of this was, what is a reaction rate when both reactant concentrations are 0.04 moles per gram cube? All right, so if we use experiment 1 again, okay, it doesn't matter this time what you actually use. So let me take out experiment 1 because you're given the values. All right, so using the values given, then your rate, you now want to find out what your rate is. You already found out your rate constant, which you got from here. So once you plug all of these into the equation, you're told that both reactants have the same concentration. Once you plug that into the reaction, then you basically just solve and you get what your rate would have been. Let's put that in. So your rate, which you would have gotten, I don't know how I forgot this. All right, so your rate, which you're trying to find out your rates now. So therefore, your rate constant times your two concentration of your reactants will have given you your rate. Any question? Use the units as shown. Any questions?
There's someone in the chat that is asking if there's a way to make sure the constant is correct.
Right, and Miss, after you finish that question, now that I'm hearing you a little bit better, the person who did ask how you get m squared, Miss. You can re-explain that, please?
Right, give me a minute. One minute, please. Give me a minute. Let me just calculate something. All right, so calculate the other one. Okay, so what I was doing was to calculate so someone had asked, how do you know that the rate constant is correct? So what I went ahead to do was to calculate the other two, the rate constant using the other two experiments, so using 2 and 3, and it's more or less, when you round it off, it's more or less the same. All right, any other questions? Hello?
Miss, I was saying that I'm hearing you better now. So what I was asking, back to where you have M squared. I heard somebody asking earlier, but I didn't hear the response.
Okay. What I did was to put in my units. I used the unsimplified rate law expression that we got. Is that what just the complex, the non-simplified one? Yeah. So remember we came up with this for the rate law. So I used this one. I guess if you had used this one, it would have been different. But I used this one, and what I said was that if you raise anything to the 0 power, you would have gotten 1. So the unit would have been, you would have had a unit.
Yeah.
1 mole. So I put that in, and then once I times molar times molar, you gave a molar square, and then divided that.
Okay, miss. All right, thank you.
Okay. Any other questions?
Not at the moment, miss.
Okay, so if not, then let's move on to organic chemistry. All right, so question 3. It says an unknown compound A one minute. So it said that question 3, an unknown compound A was found to have a molecular formula of C5H8 oxygen. Provide a structure and name of any isomer which has 1 an aldehyde, 2 a ketone, and 3 an alcohol. Did you guys do that one?
No, 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 no.
Yeah.
I was trying it, but I wasn't getting it, to be honest. Yes.
Would Penton?
Word on this.
Wait, Masuka miss, I get the alcohol one, but me also I look on the aldehyde one now.
All right, so as we know, an aldehyde have this structure, right? C Let's see if I can get it. Right? That's how an aldehyde would look, right? You
Yes,
have a
miss.
carbon double bonded to oxygen with a hydrogen to one end.
It's like an alcohol.
Hmm? So, if we use that as a skeleton, that means that we have a carbon attached to hydrogen. Double bond to oxygen. Oh, my oxygen is not looking properly. And you're supposed to have 5 carbons in total. So my R group would therefore have 4
Carbons. Yeah.
carbons.
1, 2, 3, 4.
Just fill in your cases.
Okay. And
Does everybody have this aldehydes?
Repeat that, miss.
Does everybody have this for the aldehyde?
I have had something like this. What I think 1, 2,
with
3,
this.
4, 5, 6, 7, 8.
Yes, but
We have more than
I have
more than
this,
8 more than 8
but there will be
hydrogens.
more eight. Exactly, more hydrogen will be there.
No,
Yeah.
what you know, miss? What you know? You see,
So
for
would there be a
the
double bonded
last
carbon?
the last carbon supposed to have,
Double bonded carbon.
yeah,
1, 2.
yeah.
Would have
No,
9.
wait, yeah.
You would have 10.
Yes, miss.
So there has to be a double bonded carbon somewhere.
Exactly.
Or
at the end part, right there, so the
Okay.
carbon here, no other, no oxygen not there.
It's right there.
Yes, sir, I have mine too.
Same.
let's see how much I have here now. So that's 1, 2, 3, 4, 4. There's 1, 2, 3, 4, 5, 6, 7. That's still 7.
Miss, why never just make it stay how it was and just add the hydrogen to the 5th carbon that you had? That would have made
that.
Oh, 8
That would
hydrogen.
be 9.
Yeah.
That would be 10 hydrogens.
Miss, all right, you
I mean,
That formula wrong. No, it would wrong.
What you know, miss?
Why
You
get
could
H
just draw
hydrogen?
a straight chain carbon,
Yeah.
right? And then have one at one end, you have the oxygen, the double bonded oxygen with the carbon and the hydrogen, like I'm see where you do right here, so. And at the other end, you have a double bond between two carbons. Because Marvin right
Yes.
and look at the 8 hydrogen.
So that have to be an alkene.
You would have to have, based on what I'm seeing, you would have to have an alkene on it.
Yeah, you'd have to
Yes,
have an
please.
alkene.
That's what I had.
Wait. Wow.
Right.
So the red line is a double bond?
Yeah, man, I'm going to change it.
Oh.
Just trying to see if I can get a straight chain without the alkene.
I don't see it happening without that alkene.
Yeah, that's how it's supposed to look.
Two, three, five.
Where would you guys put a double bond?
Okay, so this is it,
Is that
guys.
6
The
carbon?
double
Oh,
bond,
okay.
the double bond would be at the end. But why you have
I don't feel put in a double bond. Why?
Because it would still have 9 hydrogens.
Exact. Yes, miss.
Because each carbon is supposed to have 4 bonds around it still, so that.
So is it that the only
The double
way
bond
that,
can go on the third carbon. If you put a double bond on between the third and the fourth carbon, then you can have 8 hydrogens.
Let me see.
Doesn't matter where it goes. If it has 9 in one, it must have 9 in the other. All right, let's see now. 1, 2, 3, 5, 6, 7, 1, 2,
That looks so confusing.
5, 6, 7, 8. That's 8. All right.
Okay.
You guys see what
that's excessive though.
Exactly. It's so
Very.
much. You should have just put the long
alkene chain.
Yeah. And just put the thing in the middle, the double bond in the middle.
That does look
No,
ugly.
the thing why I don't want to put a double on is because further on in the question, it alluded to the fact that
I'm not hearing her. She break up.
why I do not want to put a double on that I
Wait,
believe
miss,
that
you're breaking up, miss.
Can you hear me properly now?
Yes, miss.
I did not want to put a double bond.
must still not get, excuse me, miss?
Hello?
Yeah, I'm hearing you.
Must still not get why you would have, because this kind of look, as somebody did say, kind of look excessive. Why would never they still not get, why would never they just have the double bond at the
On the
one at
straight
the end?
chain or on a straight
because
chain.
I write it down, I draw it, and
You get the 8 hydrogens.
yeah.
Yes, miss.
So the reason why I did not put a double bond in it is that I believe that if there was a double bond, they would have told you that it has an aldehyde and a double bond functionality. They just said that double bond.
Mister, can you repeat that, please?
The reason why I was not, as you know, I was not too keen to put a double bond in it was that I believe that if they wanted you to put a double bond in it, they would have said that it has an aldehyde and a double bond functionality. They're interested in aldehyde, a ketone, and an alcohol. Also, when you read further down the question, it does allude to the fact that their carbonyl compound does not have a double bond.
Okay.
We'll
Okay.
Excuse me, your microphone kind of low, so the end part where you say whenever you really hear it properly.
I'm saying that I would not, on the first go, put a double bond in it because it does allude. I believe that if they wanted you to put a double bond, they would have told you that there's a double bond present. So it would have said an aldehyde and an alkene functionality, or it would have said ketone and a double and an alkene functionality. It just said ketone. It just said aldehyde. It just said alcohol.
Yeah, but then it's any isomer.
True.
I mean,
that's true.
It depends on the person who's marking it, how they
Excuse?
their. But if it's aldehyde, I would not put aldehyde and alkene to be on the safe side.
Okay, fine.
But miss, if the double bond is what comes up first, wouldn't it be wise to put the double bonded carbon to form the aldehyde?
I'm not hearing you.
No, it can't. The double bonded carbon can't be on the aldehyde because it's already double bonded to the oxygen.
I mean, I understand. I'm talking about the structure overall, Andrew. Like if you
Mister, can
if
name
in
it, please?
exam under exam pressures.
Exam pressure, right?
All right, guys, there's something to do. Normally, if you see it low, if it's realized that you don't have enough hydrogens, it normally means that there's either one, a double bond present, or two. If you realize that you don't have enough hydrogens fit what you want to put, then that means that it's not just an alkene. It's not just an alkene. You can either have a double bond or you can have a hydrogen. But if you are not supposed to put a double bond, then the next thing you need to think of is that there's a cycle string.
Miss.
Wait, we can just. All right, let the person talk first. Talk first.
Yeah. What's the name of this isomer that you drew?
Yeah, the name. What's the name of the isomer?
We haven't named.
Pardon?
Named it yet.
I haven't
We
named it
haven't
yet.
named it.
Okay.
Probably some cycle or something of the sort.
1, 2, 3. Okay.
May I say with that name probably some cycle something of the sort?
So it would be first. It would be. So what's the first thing that I normally put in my tutorials when I'm doing it? Normally put on the name of the parent chain. Right? And the longest straight chain would have been what?
The 4 carbons.
Oh wait, no. Bute.
Butane.
The butane. The bute.
Okay. And then how would you go ahead? How would you go and name? All right, so just tell me some of the names you guys came up.
Mr. breaking up some fun or something is affecting. I'm not hearing.
So you know the first thing you normally put down is a longest straight chain. Hello?
We're not hearing you.
Wait, repeat, miss?
What are some of the names that you guys came up with?
Oh.
Okay. Wait, when you call it when you have like a O, the oxygen part, the double bond oxygen part again? Is that a functional group?
No.
Oh,
Made
yes,
up like butanol.
Butanol.
We have one wish wait. 1, 2, 3, 4. Okay.
Wait, the double bond O, is that a functional group?
Yes, it is.
What?
Double bond O attached to the hydrogen is an aldehyde. That's what makes it an aldehyde.
Yeah.
Cause me want to say but
Butanol.
It's
Yeah.
a butanol, yes, butanol.
Butanol.
Just
Yeah.
butanol alone?
No,
What happened to
but
the
I
C?
thought about the C that is with the two H's at the
Yeah,
end.
CH2. I
the
don't
CH2.
know. You see, because the whole structure just weird to me.
Guys, let's go back to the rule. What do we normally do the first thing?
Longest straight chain.
Then number
So what's
then
Wait,
number
but
the
is it
carbon.
It's the
one?
aldehyde, so you have to come at the end.
But the aldehyde is always on position 1.
Yeah.
Oh, we're gonna look at it.
Yeah, somebody else say one,
One butanol.
3 C
What's
cycle.
my substituent?
I don't know.
So I can't take 3 here.
And what is it? CH2, what is that? You could have said like if it was CH2, it would be a methyl.
Ethylene.
Butanol, methyl, pentane or something like that, or pentene, or tane. I don't know.
Don't complicate it. It's the same thing that you've been doing all along. What's
Okay.
your longest range? First, identify what's your substituent.
The aldehyde?
Yeah.
You want to put
So
that as a substituent?
it would be pen.
You have a cyclopropyl group.
Mm-hmm.
Aldehyde. Now let me draw it in a sketch for you. Just I have a sketch here. Come off this.
Wait, is one aldehyde viewed 3 cycle?
No, you wouldn't.
No, it would say aldehyde.
Yeah, that.
Cyclopropyl butanol? I don't know.
Yeah, something like so.
What did you say for the last part?
Butanol. No,
It wouldn't be butanol.
would have been
It would be a
butanol.
pentane because it's 5 carbons.
No, but the longest chain has a but.
It would be, I think said the cycle something would end up on 3, no sir?
Yeah.
Yes.
You would have been on what, 3 or 2?
3. Cycle.
3.
3.
Cyclo. I don't know. So you're that. Oh my gosh.
I think, yeah,
So
man,
would
it's
it be 3 cyclo? Would it be 3 cyclo, 1 butan?
No, but then wouldn't it
wouldn't
have
be
to go in
butanol.
alphabetical order?
Yes,
butanol, 3 cycle
So
something.
then the butanol will have to come first. I'm confused.
Same.
Exactly.
Confusing yourselves.
1 but.
This is what we have. Can you guys see my screen right now?
Yeah.
Yes, miss.
All right, so this is what we have. Let me see if you guys see it a little bit simpler here. Always go back to your basics, what you know.
Okay. Which would it be? 1 butanol, 3 cyclopentene, artane, or something like that?
That sound correct to me.
Would that
1
be
butanol.
3 cyclopentene?
If you have 1 butanol, and that means that your substituent has 4 carbons, and your parent group pentene has 5. That's 4 plus 5 is supposed to have at least 9 carbons in your substituent, in your compound. That's not what we have.
So 1 butanol, 3 cyclomethyl.
So miss,
That's the C and the.
So miss, what's the answer, miss?
Yeah, what's the answer?
Yeah, what's the
answer?
Let's go back to what we need, right?
Okay.
Let's go back to what we need. Naming our longest straight chain, right? 1, 2, 3.
Yes, miss.
All right, what's my substituent here? My substituent is Liz.
Okay, yes, miss.
Is something else happening? Because I just seen the PowerPoint.
You see the PowerPoint?
Oh, okay,
There's a
cool. Never mind.
my substituent in my cyclic group, that small cyclic group right there, right?
Mm-hmm.
If I block that out, what's my longest pairing chain right there? The
Butane.
Is that butane? I block out my substituent. What's that group?
Excuse me, miss.
Oh, wait, is it? If you
Um,
block the substituent, it would be butanol.
No,
I think it would be butanol because
Am I
the cycle
supposed to
is
be
of the
seeing?
three. The three
Okay, that means you're not seeing
carbon
my
them,
screen.
right? And this of the two. No, sir?
I'm not seeing your screen, and miss. I'm just seeing
We're
the.
stuck on page 13.
PowerPoint.
Yeah.
You guys had just seen the PowerPoint?
Yes, miss.
Yeah.
My bad. I thought you were seeing my screen.
If you minimize the PowerPoint.
Wait, excuse me, miss. The cycle group right there, so or we wouldn't call that. That consists of the three carbon them, right? So it wouldn't, and the next group wouldn't consist of the two carbon.
Yes.
So it wouldn't. When I think it would be butanol, then it would be one.
Propanol.
Ethyl.
Ethanol.
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 One ethanol.
So we don't
Cycle.
count.
Cycle.
So we don't count the carbon in the cyclopropane.
Yeah, apparently we don't count that.
No, how would you count that?
Oh, okay.
Wait, is it one ethanol, three cyclo?
One ethanol?
No, wait.
It would be. It would be.
So it'd be one.
It would be two cyclopropane.
Two or three?
No, two, because the aldehyde is on position 1.
Yeah.
All right. So
the cycle is on number 3.
It would be what? Guys, you know, let me just answer it. All right, so that's confusing yourselves. All right, so what we do know is that, right? We have renamed our longest parent chain. The longest parent chain right now is group. One person was answering it correctly. That's my longest parent chain.
Oh.
So therefore, this becomes my substituent. It's just like if you had another like this. Let me see if I can put it there. You had different per se, right? You would put your cyclopropyl on your second carbon. The only thing that's happening now is your cyclopropyl is on your first, is on the end. I don't want to see it first. The cyclopropyl is on the end of your carbon.
For a second carbon.
End of your carbon.
Cycle.
So it would be cyclopropyl ethanol.
Yeah. So that's the only thing that's happening right now. Your cyclopropyl is at the end. You know that you number when you're dealing with aldehyde, you're dealing with acid, you start to number from the position where you can give a functional group.
Okay.
The lowest possible number. Therefore, you're going to number from this end, 1, 2. That means that your parent group has 2 carbons, and that's ethanol. E. Let's see if I can just make some notes. Let me just erase these and make some notes. All right. All right, so ethanol. I'm not seeing my pen coming up. So you know that your parent group will be ethanol. Therefore, look at your substituent. The substituent is simply a cyclopropyl. and it's on carbon number 2. So it's 2-cyclopropyl ethanol.
Oh, okay.
Exactly what you guys normally do. Just don't get confused by how the structure looks. Just go back to your foundations.
Okay, got you, miss.
Okay. Okay.
Okay.
Repeat the name, or you gonna write it down?
2-cyclopropyl
Propyl ethanol. Propyl ethanol.
Yeah, propyl ethanol.
Oh.
Just don't get confused. It's on number 2, which is why it looks like that at the end. And your parent group, you group with the functionality. Aldehyde, and that aldehyde only have 2 carbons. That's ethanol, not ethanol. What about if we had a ketone? That means that you're not going to press on this one now.
Would it not be the same thing? No, never mind. Never mind. Forget I said that.
Oh my gosh.
Because, all right, so the ketone is the one with the
double bond on the 2 R group, double bond oxygen,
2 R groups,
and the double bonded
oxygen.
oxygen.
1, 2, 3, 4. How much carbon have I again?
Wait, repeat again.
You
Where
have
is it for the
between
ketone?
5 carbons working with.
5
6,
carbon.
7, 8.
Somebody could repeat again for the ketone part, where them said the 2 double bond and 1.
And 2
cyclopentone.
Yeah, you could have that. 1, 2, 3, 4, 5, 6. Yep.
Excuse me, miss. You
I
could
didn't write it yet. Okay.
Excuse me.
So someone said cyclopentone, right?
Yeah.
Yes, miss.
My pen not coming up. Oh. Right. You know there's a separate cycle, there's a pentone. That means that it is 5 carbons in it.
Yes, miss.
And the fact that it's a cycle, you realize you don't have a substituent. So therefore your entire compound is with a double bond on one of the carbons. I can't get my pen off. And then the alcohol would be easy.
COH.
Miss.
Yes.
Sorry, I was doing something. You answered the question for ketone already?
There's a cyclopentone, but my pen not working. I can't draw the structure. I don't know why. It's not allowing me to draw it.
Oh, so.
I think I'm on this ketone thing already, you know. Wait, I'm see if this.
Oh, was it working?
What do you have for what do you have for alcohol?
Can't find my knife. Where's my knife?
What do you have for the alcohol?
Confused. That's what I have.
Huh?
You have cyclopentone.
For the alcohol. I can't hear you. What do you guys have for the alcohol?
Cyclopentone.
Cyclopentone.
No, never mind. Forget I said that.
Wait, so what's the name of this?
Cyclopentone is the one for the ketone.
Cyclopentone?
Yeah.
Thank you.
You can't be cyclopentone. Cyclopentone has.
That's why I said forget I said it.
Oh God.
Oh my gosh.
I had a straight chin, but then that has a.
If you recognize that you're deficient in in hydrogen, then it's either that you have a double bond or you have a cyclic group, right? So we know that we're not using this. We know that we have to have cyclic groups. So if you say cyclic group and you realize that, then what about trying? I can't get my pen up.
Canada, you keep breaking, you keep going in and out.
Yes.
Really? Sorry.
Yes, miss.
Let me tell you. All right, so remember when I said that if you realize that you're different in hydrogens, you either have a cyclic group or you have a double bond. Since we're not using double bonds, right? Since we're not using double bonds, we know that we
Miss, you're
must
breaking
have some cyclic. I'm still breaking up?
Yes,
Miss, Miss, you're breaking up.
I don't know. I'm hearing you guys fine.
You're in
Are
and
you
out.
hearing me better now? Are you hearing me better now?
Yes, miss.
Yes, miss.
Set aside the microphone. All right, so if you realize that you're deficient in hydrogens, it's either
Yes,
that you
yes.
have an alkene or you have a cyclic group. We
Yes,
know
yes.
we're not using an alkene, right?
Okay.
So that means
yes,
that you must have. You went ahead and you put cyclopentanol, right?
Really?
Pentanol, that's alcohol. That's for the alcohol. And you got 10 hydrogens, so you know you cannot have that. That means that you need to try to downsize your cyclic group. If you downsize your cyclic group, how many hydrogens do you get? Butanol.
Checking.
Yeah.
1, 2, 3, 4, 1, 2, 3, 4, 5.
4, 5, 6, 7, 8.
8.
Oh, okay.
However, what's the problem? There's a problem there. You have 8 hydrogens, but what do you have? What are you deficient in?
The oxygen.
Oxygen.
The oxygen.
Carbon.
And
What,
the
miss?
carbon, yeah.
Carbon. You only have 4 carbons.
Right.
Oh, so that means you're going to have to put a branch to attach another carbon. But then,
Wait, excuse me there, excuse me
I
there.
understand.
May I go, miss, may I go on sort of the, we call it again, video, so you can see when we write? Because I do all of them. But basically, if I think I'm going to get every one of them right here, so.
Okay.
Right there.
I can't see. Oh, God. All right.
Yeah, see?
Are you sure?
Yeah, I'm seeing now.
Yeah. But it kind of blurry though.
Yeah, blurry.
Blur bad.
Oh, wow.
You can't see that.
Yeah, see?
No, sir.
I see that.
Can no, sir?
Yeah, it's blurry. Yeah, we'll see.
For the ketone, well, you're moving the book. Wait.
Focus it back now. Yeah, we see the ketone.
Mm-hmm.
Yes, for the
Let me see the
ketone.
ketone. No, the ketone is off.
Yeah, it is.
Ketone is off because you have 2. Remember, the N hydrogens have to have 3.
Yeah.
Yes. I just realized.
Ketone be a cycle.
Come on for this now.
Just turn off your camera.
Go to the bottom and click end video. Yeah.
Okay.
No, it's not off.
Oh.
All right. Yeah, it's good.
Yeah, but I want to know what you got for your alcohol. So why you came off it?
She wants to see what you got for your alcohol.
Oh, wait, may I come there?
Just to repeat, for the ketone, you say cyclopentone, right?
Yeah.
Yeah.
What's the fix about the ketone? I just realized I said this other. You said the alcohol?
No.
It's
blurry.
You have to put it closer.
Alright, tell me which one you say.
The
ketone.
Ketone. Aldehyde, alcohol.
Alcohol.
So let's do the alcohol there. 1, 2.
Yes, you see alcohol?
Yeah.
Oh yeah, that looks right.
Oh, you put the double bond in it.
Yeah.
Yeah.
Yeah, I have a double bond.
Oh, one thing though.
Yeah, that's what I have.
Want to show you the aldehyde we might have because we still not understand the aldehyde thing. So I just remove. You see aldehyde?
Yeah, I'm missing that.
Yeah, my aldehyde wrong or it can
And
Not
okay.
wrong person, but
I keep changing.
I can't see the end. I can only see the alcohol.
Oh, I see it now.
Okay, put the double bond in it. As I said,
Repeat.
I'm not sure if your lecturer would accept it with a double bond. At first chance, I would not put it in it. If I can get an aldehyde that doesn't have a double bond in it, I would prefer
Yeah.
to use an aldehyde that does not have a double bond in it.
6, 7, 8.
But
For the alcohol, I still
someone point out it's any, they said any isomer. So, I mean, if I would have to ask Dr. Gallimore, one of the lecturers, how they would mark it. So I could probably ask them and get back to you guys with it.
Yeah.
Okay, miss.
Okay?
Yes, miss.
alright,
Because the alcohol is challenging without a double bond in it.
right.
Exactly. Yes, miss.
So I could ask them if they would expect to see if they would give you it with a double bond and then get back to you, like Danielle, what they say.
Yeah, you can either send the question. Is it this specific one? Question 3.1 and then part 3.
I would. I will.
Hmm?
I will.
4, 5.
Okay.
All right. So, because the alcohol is challenging without using a double bond.
Yes, miss.
But as I said, first class, if I can do without using the double bond, I would. Perfect. But I will ask. All right, so let's move on to part 2 then. How would you use an IR spectroscopy to determine if compound A was a carbonyl compound or an alcohol? How do you use, what does IR spectroscopy tell you? How do I get this? My computer
the amount of light like that's observed, I guess, or passed through the substance or something like that, I guess. I don't know.
Gives you, it tells you information about the different bonds, right?
Oh.
Based on how the bonds vibrate, you can tell that it's very specific. It can tell you if you have a carbonyl bond, whether or not you have a C double bond O, or whether or not you have an alcohol, etc. I can just get my computer to move. My computer is freezing up, I don't know why.
Michelle, don't have to have the chart to tell you the
Yeah, no, I
IR
have the chart on this.
for each bond. Oh. Michelle just asking because there was a tutorial and it didn't give us the chart, so I was confused.
No, but you could just Google the chart. I just
Yeah,
my computer is
that out
freezing.
after.
Guys, my computer has frozen, so I
Oh,
cannot.
God.
Oh, what will we do?
Pick it up tomorrow.
Oh my gosh.
Not moving. What I could do if it doesn't come up, if it doesn't unfreeze soon, is to send you guys the answers. Okay, let's see if it comes up.
Okay.
Okay, so I guess that's it. It's not moving. Let me see,
Why?
1 minute. About my screen, let's see if I can
For
unshare and then see. It's not even allowing me to unshare my screen. I don't know, just froze.
Okay.
Okay.
It working?
So computer is frozen, so
Oh.
I can't move the screens. Alright, what I could do is just walk in.
I can stop your share screen and then restart it and see if that works.
Okay.
It unfreeze?
Yeah.
All right, cool. You can start the screen back when you're ready.
Are you seeing it?
No.
No, we're not
It
seeing
takes
the
a little while.
screen. Okay.
Are you seeing it now?
No, miss.
No, miss.
Wait, what just happened?
Yes, it's doing the credits.
Oh, she took her share screen off in order to restart the thing so that we could continue the
That's her computer
questions.
froze.
Yeah.
Alright.
Alright, Missy, I think you're coming back.
Yes, miss, we can
Yes,
see.
miss. We can see.
All right, cool.
And we are back.
Okay.
Yeah, we're good
This
now.
is what you actually get. So the IR table.
Yes, miss.
Mm-hmm.
The IR table will normally give you information on the different bands, right? So
Yes,
if you
miss.
have a nitrogen, would expect to see a band, a medium intensity band, around 200 and 2,200, so around here. If you're looking for a nitrile group. If you're looking for an alcohol group, that would be a C double, that would be a C, that would be an OH group, right?
Yes,
As you
miss.
can see right here, the OH group would normally come at 3,650 to 3,200.
200.
That's where the alcohol would be.
Yeah.
So that's where the alcohol would go, right here. So is that nice group?
Yes,
right
miss.
here?
Long dip. Yes, miss.
Yes, miss.
And it is normally strong, but it's normally a broad signal. So it's not as pointed as these, normally a broad signal.
Okay, miss, got you. Yes, miss.
Carbonyl. Carbonyl is a C double bond O, right? So
Yes,
this is where the
miss.
C double bond comes, and it would be around 700. So, and as you see, it will be a strong and it will be a very intense peak. And that's
So
what
that
we'll
would be
go
right
in
here.
for.
So, yes, miss. I see it.
So that's how you would use the IR to differentiate between whether or not you have an alcohol from when you have a carbonyl from if you have, let's say, an alkene, right? And usually you can tell the difference between, you can start to tell whether or not you have aldehyde as opposed to ketone. You have more specific features than these. There's the OH group of all the C double bond. Normally, for an acid, the C double bond O for an acid is around 1650. That's the one that's around 1650. And aldehyde is around 1725. So it's not as grouped as, it's not all grouped into one as is stated here. They normally differentiate between an ester from an acid, from an aldehyde, from a ketone. But for your life, you can just group all of them. Once the C double bond O is coming in this range.
Okay, miss.
So if you look at spectrums and if you run your IR spectrum on your compound, if you don't see it having that nice strong peak in your 1700s, then you know you don't have it.
Okay.
It's not uncommon.
Wait,
You see it having this nice peak.
You could repeat that part, miss? We're about the strong peak.
All right. So what I'm saying, you have a compound, you don't know what it is. It could be an alcohol, it could be an carbonyl, right?
Yeah.
Use IR to tell which one you have. You would run an IR spectrum on it, right? I'm not sure if you guys have been privileged enough to go up to the IR room in your labs, I'm not sure. But if you have, and for those of you guys who did sixth form and came to you would remember that workshop that we did in the IR room. So once you run a sample on your IR experiment, on your sample, you will get a printout looking like this, right? Where you have a number of different bands showing up. Where those bands show up tells you a lot of information about the compound. So if you have a compound with a band that shows up at 1300 to 2500, 2600, 3200, that's in the alcohol region. You know that your compound has an alcohol or OH in it. If it comes up at 1700, you know your compound has a carbonyl group in it, right? So depending on where your bonds come up for your compound, it gives you information on the structure of the compound.
Okay.
You guys all understand?
Yes, miss.
Yes, miss.
Yes, miss.
Yes, miss. So compound A does not decolorize bromine solution, nor show any reaction with phenylene solution. Is that what I have there? Nor show any reaction with phenylene solution. What is a likely structure of compound A? First and foremost, what does phenylene
Can come
test?
off of
What
the
does
screen. The video thing. Wait, can it? Okay. Sorry. Continue.
All right, so what does phenylene test or phenylene, depending on how you pronounce it, what does that do? Have it there. It's used to determine the presence of aldehydes, right? Or carbonyl. So that if it doesn't show, if it doesn't decolorize bromine, what normally decolorize bromine? So if you have a reaction and you're testing for the presence of functional groups, and you tip a little bromine water in your compound, and you don't see it going colorless, it doesn't decolorize bromine, what does it mean? What does that mean about the structure of a compound? It means it doesn't have a double bond.
No, miss.
Right?
Repeat, miss.
It means it does not have a double bond in your structure.
Oh, because only when it have a double bond, it can decolorize a bromine. So if I have an
Yes,
alkene.
bromine has a double bond.
Oh, so alkene
Right?
colorizes. Okay.
So you know you don't have an alkene present. And if it doesn't react with phenylene solution, then you know you don't have an aldehyde either. So what you would have would be alcohol without a double bond.
A double bond.
Right?
Yes, miss.
Yes, miss.
So would we then have to, for this question, it says what is the likely structure of compound A? Would we have to draw out the structure of compound A?
How much was the marks again?
How
much marks was it?
Checking.
If it's like 2 marks, then I do it. 4?
2 marks.
If it's like 2 marks, then I doubt it.
Okay, miss.
Okay, miss.
All right.
And you could draw it if you have time.
That's all I
But
needed
it
here.
order like a structure. They say what. Right?
Yes, miss.
But to be on the safe side, you can draw it. All right. B, I'm probably not gonna get to do number. I'm probably gonna have to just send you guys the answer because it's now 3 o'clock.
Okay,
Right?
miss.
Curfew.
Number
Right.
Okay, miss.
part B. So I'm just gonna go through these and I can send you guys the answers.
Okay.
So moving forward, you asked what is the following transformation? How would you carry out the following transformation? And you're told to know that more than one step is required. So you have a double bond, and you're going from a double bond to an carbonyl. What do you think would be the first thing that you would have to do?
Break the double
This is
bond.
a 2-step. So
Yeah,
break the
two-
double bond and make what? Would you hydrogenate it? Would you oxidize it? What?
Wait there. So
The hydrogenate it. Okay.
If you hydrogenate it,
Yeah.
you're going from a double
Add the
bond to
hydrogen.
alkene. Alkene.
Oh.
Yeah, but
Yes.
what do you know about alkanes? They're highly unreactive. So how would you move from an alkane to a carbonyl?
Yes, so we call it like a when they take out the hydrogen and so.
Substitute?
No, I don't
What
substitute.
about
Subtract.
adding
Elimination?
what about adding an OH group to it? So we know we can move from an alkene to alcohol, can't we?
Mr. breaking up, you know, and not hearing.
Yes.
I'm breaking up for everybody.
Yeah, yes, miss.
Yes, miss.
All right. So moving from an alkene to carbonyl. You guys are saying that you would hydrogenate it. But remember, if you hydrogenate it, hydrogenation means you're adding hydrogens.
Hydrogen. Yes.
That means that you're separating that double bond. That will mean that you're adding hydrogens to this. And you don't want that. If you add the hydrogens to both of it, then you are basically making an alkene, and you know that alkenes are highly unreactive.
Okay.
That would finish your reaction right there. What about adding an OH to it using Markovnikov? The Markovnikov is that you're adding hydrogens to the carbon that already have most. So you will use anti-Markovnikov. Because you want the OH to go on this hydrogen, on this carbon, while the hydrogen be on this one. You guys see that?
Yes, miss.
What does Markovnikov?
What is that?
Markovnikov rule.
Is it
Yeah,
that
what does Markovnikov say?
that is so damn good? You know, I'm not answering this. But something with like the amount of
In
hydrogen.
the yeah,
The carbon that already have
the most
hydrogen.
most hydrogen atoms. Yeah.
Yeah.
Good. So if you add the hydrogen, if you use Markovnikov rule, and you add the OH to it, let's say sulfuric acid, right?
Yes, miss.
Then that would have meant that your hydrogen would have been added to carbon number 1 or to carbon number 2. So your hydrogen would have been added right here,
Yes, miss.
right?
Yes, miss.
And your OH would have been added here. Now, is that how our structure is?
No. See, I'm with anti-Markovnikov.
You would have had to use anti-Markovnikov, because if you use this, when you try to make your carbonyl, you're going to get something like, it won't even go to your carbonyl, because it can't, you would not be able to get, and you can't change a parameter, right? So
Yes,
what
miss.
you would have to use is anti-Markovnikov, where you use borane, otherwise called hydroboration.
To be honest, miss, you kind of still a breakup.
The
So,
HBr
like,
minus. The HBr minus.
Right, so I would add my hydrogen to this carbon using my hydroboration reaction.
Hydroboration.
Oh, sorry.
Hydrobromination.
Hydroboration.
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 Using borane.
Oh, okay.
Right? And then once you have that
HBO.
for you to move now from your alcohol to your ketone. What do you use to move from an alcohol to a ketone?
Alcohol to ketone.
Domination.
Remove.
You could use chromic acid, right? Guys, just go back over.
It's all blurry, yes.
I'm going to send you a note. I'm going to send you notes on these. But just go back over your lecture notes as well. They're there. All right?
Okay.
For this one, you're moving from a... When you look at the difference in the functional groups, right? So when you look at the difference in your functional group, this is a ketone. However, you have an alcohol here. And then you have a bromine here. But then you have a alcohol here. So the first thing I would do would be to do a substitution reaction where I substitute my bromine for alcohol.
With the alcohol.
Right? And we do no substitution reaction.
Oh, then it goes up. Yes, miss.
And then you reduce your ketone to your alcohol.
Yes, miss. You can use lithium borohydride for this one, for that part.
For the reduction?
Yeah. To form the second, put on this next OH.
Alcohol?
But you
Yeah.
also, you could. Right?
Yes, miss.
And then number 3, you're moving from, what do you recognize about number 3?
It's an aldehyde, alkyl halide to aldehyde.
Yeah, alkyl halide to
But you're not
aldehyde.
alkyl halide. That's not the only thing that's happening.
An alkane to an aldehyde.
Here. And look at this, guys. You had 4 carbons here, but now you only have 3.
Oh, okay, so there was an elimination.
Yes.
Okay.
Right? So the first thing that I would probably do, I'm thinking about how do I get rid of some of my, you have to think about all the reactions that you know that you can use to get rid of your get rid of carbons, right?
All right. Yes, miss.
So the first thing I would probably do here is to form a double bond. Form a double bond, I get a double bond right here. And then, let me see if I can erase, let me see if I can do this.
So if we move the double bond, if the number 1, elimination, number 2.
So if I,
What happened?
Sorry.
You're off.
Yeah, I'm coming back.
Okay.
Oh my gosh.
No.
That's what you said, form a double bond or something like that?
Yeah, should form a double bond and that's for sure.
So form a double bond to get rid of the hydrogen.
Yes, form the double bond to get rid of the chlorine. So you're gonna have butene right now, right?
Yes, miss.
1 butene, the double bond is gonna be on the first carbon. And then, how do you know you get rid? How do you know you can split a double bond?
O's analysis? I don't know.
O's analysis.
Yeah.
And what kind of workup would you have to use? Because right here, you're realizing that you have an aldehyde and not a hydroxyl. And a carboxyl. So if you have an aldehyde, that means you have to use reductive workup.
Okay.
Right? So, and then that will split your double bond in 2. If you are aldehyde on this side, and then you will form a minor product. You will form another product of here, but that's not. You form, yeah, that's not major. So I will give you guys a worksheet with this, and I will probably send it to you over the weekend.
Okay, miss.
Please.
Okay, miss. Thank you.
Hope it was helpful.
Really, really helpful.
Thank you very much, miss.
Yes, miss.
Feel
Respect.
more prepared. Appreciate it.